Hello friends, this is part 2 of uh, electromagnetic theory question paper solution of 2023 BSc 6M of Dibrugarh University, and we have already solved the MCQs in the last video, right? So today we're gonna start from question number 2. So question number 2A, what is displacement current? First, let me explain this. So now you see, when current passes through a conductor, we know that a magnetic field set up around the conductor. Okay, right? Now you see, Maxwell, postulated that not only this, that current in a conductor produces magnetic field, but also changing electric field in vacuum also produce magnetic field, right? For example, now you see, let me tell you like this. Suppose this is a capacitor. During the charging of this capacitor, what happens? The change of electric field takes place between these two plates, right? And this, change in electric field, produces the same magnetic effect as the ordinary current, as an ordinary conduction current does. Okay, and due to this change in electric field, we get displacement current. Okay, so now let me write the definition. Let me write the answer here. To displacement current, right? So this is the answer you need to write. Okay, so now let's move on to the next question. Take the screenshot, and or you may pause the video, or you can note the answer. Okay, so next question is, what are momentum density and angular momentum density? So now let me answer this question to B. So here you see, to be answer, the momentum density is given by pointing vector S divided by c square. C is the velocity of light in vacuum, you know that, right? So I have not mentioned here. And the pointing vector S is also can be written by 1 by mu naught E cross B. E means electric field, B means magnetic field, right? We can write that way. So do mention the terms, okay? Which term, meaning of the terms, okay? Now you see, also we can write, we know that C is equal to 1 over root over mu naught epsilon naught, right? So C square gonna be equal to 1 by mu naught epsilon naught, and if you use that value here, then what you're gonna have? Then you're gonna have epsilon naught E cross B. Okay, this gives momentum density, right? This gives momentum density. Okay, now let's discuss about angular momentum density. And angular momentum density now you see, we know that angular momentum is given by r cross linear momentum, right? Okay, so here you see what we can do. Actually, angular momentum density, then using this, what we can write, this is angular momentum, that is position vector cross linear momentum, right? So when we say angular momentum density, that will be position vector cross linear momentum density, which is this one. Linear momentum density is this one, so we can write epsilon naught r cross E cross B, right? E cross B. So r is the position vector, right? So E is the electric field here, B is the magnetic field. Hope you know these things, right? Okay, let's move on to the next question. What is the next question? Define relaxation time. So we need to define relaxation time. Question number 2C, answer relaxation time. Any distribution of charge rho naught, this is the original charge, suppose, decays exponentially at a rate which is independent of any other electromagnetic disturbance which can be expressed this way, rho. So this is the original charge distribution, rho naught e to the power minus t by tau, where tau is nothing but epsilon by sigma, which is called relaxation time. Right, now you see, let me explain it in details. So here you can see, we know the equation of continuity. This is the equation of continuity, right? So now, and vector form of Ohm's law is this one, right? And Gauss law in dielectric, so this is the Gauss law. In case of free space, we used to write epsilon naught instead of epsilon, right? So now if we multiply both sides of this Gauss law by sigma, then we used to get this. Then this can be replaced by J using equation number 2. Then this divergence of J, that can be replaced by this. So I have put this one here. Then we have got this, right? Now separating the variables, so we have got this step. Now let us integrate this. Integrating, we have got this. This is natural log ln rho minus sigma by epsilon into t plus natural log rho naught. Okay, so if you bring this one to this side and if you use the property of log, then you're gonna get this, right? ln rho by rho naught, and which can be written in this way, right? Because when we say ln, that is log, here base is e is the base here, rho by rho naught, right? And this is equal to minus sigma by epsilon into t. So that's why e to the power this one is equal to this one, right? This is what we have got, right? Which can be written this way. Okay, this epsilon by sigma is the relaxation time. Okay, so hope you have understood this, and you can define this relaxation time this way, that relaxation time is the time, relaxation time is the time in which a charge placed in the interior of a material to drop to e to the power minus 1, that means 1 by e percent of its original value. This is the definition. Okay, so now let's move on to the next question. Next question, 2D, state Brewster's law. So now you see, so according to this law, let me explain. Suppose this is a this is the boundary between two dielectric medium. Okay, so this is medium 1, suppose this is medium 2, and this is the incident electromagnetic wave, suppose, and this is the refracted wave, and this is the reflected wave. Now you see, so for a certain angle, for a certain incident angle, theta, angle between these two, refracted and reflected wave, that will be 90, and so the angle of reflection, angle of incidence is equal to angle of reflection, and this is suppose angle of reflection theta r dash, suppose. So then theta r plus theta r dash is also pi by 2. If this is pi by 2, that means 90, right? So instead of theta r, let me write this theta I, because incidence, angle of reflection and angle of incidence equal. Let me use here theta, or just wait, let me use here theta 1 and here theta 1, so it is suppose theta 2. So the angle for which this the incident angle for which this theta 1 plus theta 2 will be pi by 2, this incident angle is called Brewster angle. This is suppose theta b, it is denoted by theta b or theta p as well, right? In that case, if the electric field, now you see, if this is electromagnetic wave, so in case of electromagnetic wave, this is the if this is the direction of propagation of electromagnetic wave, then if electric field varies this way, increasing then decreasing like this, okay, then again increasing in opposite direction, then again decreasing this way. This is the electric field, variation of electric field, then the variation of magnetic field will be in this direction, right, which is right angle to the electric field, like this way, right? Okay, if this electric field is parallel to the plane of incidence, this is the suppose direction of electric field, variation electric field is varying in this way, like this, which is parallel to this surface of incidence here, plane of incidence. Plane of incidence means the plane where this three wave, incident, reflected wave, and the normal, also the refracted wave, they all lie on the same plane, and that plane is known as plane of incidence. And for you, the screen of the device that you have you are using to watch this video, that gonna be the plane of incidence. Now you see, if the plane this E is on this plane of incidence, that means parallel to the plane of incidence, this parallel component will not be reflected. Then you see, this parallel, if this E vector is parallel to this plane of interference, then it will not be reflected, okay, at this angle. Okay, if the angle of incidence is theta b, that means it is equal to the Brewster angle. Okay, if this is perpendicular, now if this E vector is perpendicular, that means this way, perpendicular to the screen, then it will be reflected. If it is parallel, that means if it is in the plane of incidence, then it will not be reflected. Okay, so hope you have understood this. So now let me write the answer. So now let us suppose this is an unpolarized electromagnetic wave like this. Let me consider this is angle of incidence theta 1, and now you see we know angle of incidence is equal to angle of reflection, so let it be also theta 1. So this is the incident wave, and this is the reflected wave, and this is the refracted wave, and this angle is suppose theta 2. Okay, so this is here you see, let me consider here E1 is the electric field vector associated with the incident, and E1 is associated with the reflected wave, and E2 is associated with the refracted wave respectively, and these three are expressed in this form, right? Hope you can see here. Okay, now you see the reflection coefficient, Fresnel equation for E vector parallel to the plane of incidence. Parallel to plane of incidence means if the the electric field is plane, the component for parallel component of the electric field. Parallel component means, so now you see the plane on which these all three waves lie, that means incident, reflected and refracted, they and the normal as well, both lie on the same all of this incident, reflected and refracted, as well as the normal, all of this are must be on the same plane, and that plane is known as plane of incidence. And if the electric field vector, if we consider the component which is on the plane of incidence or parallel to the plane of incidence, now if I draw this way only dot, that means it is perpendicular to this plane. Plane means the plane of incidence doesn't mean this line. Okay, plane of incidence doesn't mean this boundary which is separating the two medium. Okay, plane of incidence means the plane on which this three wave and the normal lie. Okay, and this is medium 2, this is medium 1, and let me take this is the medium of refractive index of N2, and this is the refractive index of medium of refractive index N1. And in that case, if we consider the parallel component which is parallel to the plane of incidence, okay, that means you can consider if the electromagnetic this electric field is vibrating this way, which is on this plane of incidence, right? So in that case, if this is unpolarized wave, then electric field component will be in this direction also. If you imagine that electromagnetic wave, unpolarized wave is coming out of this screen this way, then you can get this electric field in this direction, in this direction, in this direction, in this direction. And in case of electromagnetic in case of electromagnetic wave, the magnetic field is perpendicular to the electric field. This is B field. Similarly, you're gonna have in this direction also electric field, so corresponding magnetic field is in this direction. Suppose similarly you're gonna get electric field in this direction, corresponding magnetic field is in this direction, suppose. So this is unpolarized electromagnetic wave, you can consider it that way. And for the parallel component, the component which is parallel to this plane of incidence, at a certain angle, for a certain angle of incidence theta 1, if the sum of these two, theta 1 and theta 2, becomes pi by 2, in that case, if you put here pi by 2, then it's gonna be not defined infinity. If that is not defined, right, so then it's gonna be 0. If that is the case, that means this parallel component, which means if an unpolarized wave incident at an angle pi by 2 minus theta 2, which is denoted by theta b, then the component of E in the plane of incidence, which is parallel to the plane of incidence, will not be reflected. And this angle is known as Brewster's angles. Okay, Brewster's angles. And now you see here, if this is unpolarized wave like this is the in this way, this is the electric field, and this is the parallel component, and this dot represents the perpendicular component, suppose, right, like this way. Then this reflected wave will be plane polarized. Here we're gonna get the perpendicular components only, not the parallel components. Okay, and here we're gonna get both parallel and this perpendicular. It is partially polarized. This is partially polarized and this is plane polarized. That's how we're gonna have. Okay, so here the incident angle theta 1, for which theta 1 which is equal to pi by 2 minus theta 2, is called Brewster's, this is S, okay, Brewster's angles, angle of polarization denoted by theta b, right? And from Snell's law, we know refractive index n2 of medium 2 by refractive index of medium 1 n1, which is equal to sine theta 1 by sine theta 2. And we know that theta 1 plus theta 2 is equal to pi by 2. To obtain the plane polarized reflected ray, this condition should be satisfied. In that case, this theta 2 must be equal to pi by 2 minus theta b, because theta 1 is theta b when this condition is satisfied, right? So that's why I have replaced the theta 1 by theta b. Okay, and theta b plus theta 2 is equal to pi by 2, and then we can write theta 2 as a pi by 2 minus theta b, and pi by 2 minus theta is cos theta, sine pi by 2 minus theta is cos theta, so here we have cos, so it's gonna be 10 theta b. So theta b is equal to this, right? So if the incident angle or angle of incidence is theta b, which is equal to 10 inverse of this n2 by n1, then the reflected light is plane polarized. This is known as Brewster's law. Okay, so hope you have understood this. So now let's move on to next question. Next question, distinguish between uniaxial and biaxial crystals. Okay, let me write the difference. To E, so uniaxial and biaxial crystals. So now uniaxial crystals have one optic axis, and it this biaxial crystals have two optic axes. Example, quartz. You can give the example of uniaxial crystals, quartz, and biaxial crystal you can write mica. So this is the answer, answer to question number 2E. Okay, now let's move on to next question. So what are step and guided indexes? So now you see, I think either it may be printing mistake or so the book that I used to follow for fiber optics, here it is written instead of guarded index. Okay, so I don't know that guarded index is also known, if the guarded index is also known as guided, or it is, maybe it is either it is a spelling mistake, or guarded index is also known as guided index. I'm not sure about that, but I'm gonna give you the answer. Okay, because I haven't got this term in the book that I used to follow. Okay, so let me write the answer. So here is the answer to 2F, step index. Take the screenshot. Okay, and next one is guarded index. This is the definition, right? So, and the meaning of the symbols that I have used here, those are mentioned here. Okay, take the screenshot. So remaining questions will be solved in the next video. Thank you for watching. See you in the next video.